Now, today we're going to look at what is lift coefficient and drag coefficient. Now, basically, you recall what is the equation for lift. Lift equal to half rho u squared CL A. A is the area, rho is the density, u is the velocity, CL is the lift coefficient. Lift is L is a lift. So you can rewrite this equation into CL equal to L divided by half rho V squared A. Okay, you do the same for drag. Drag also same, only what is different in the equation if you compare side by side with the left hand side lift equation. If you look at drag equation, the only differences is the CD or the drag coefficient. Okay, it's a drag coefficient. So you can write CD equal to D divided by half rho V squared A. Again, recall an important concept on lift and drag. Let's break your axis into X and Y. Let's say you are having a U in X direction. How do you know whether the object is generating lift or drag force? Force that go parallel with the velocity, you're generating drag. Force that go 90 degree to compare to the velocity, you get lift. Huh? So lift and drag is depending on the velocity direction. If the force is parallel to the velocity, then you will get drag. If the force is perpendicular or normal to the velocity, then you get lift. So depending on the direction. Okay. So although you see on the slide here, CL and CD, the equation is same, almost same. The differences is the lift and drag. So how do you define lift and drag force? Is depending on what we covered just now. Okay, is depending what you covered just now. Okay. Then recall Reynolds number calculation, rho V D divided by mu. In this case, we use L. We change the diameter into L. This one is for external flow. Okay, Mach number equal to U divided by C. And in this module, we just touch and go on the front number. Front number FR equal to U divided by square root of G times L. L is the characteristic length. So as front number always deal with the wave. So if you see a ship, okay, a ship on the sea. So as this ship move across the sea, you will see a wave generated by the body. So this front number is important when you are generating wave. Okay, so for this module, we were not looking into front number. Okay, but you have to know or you heard front number before. All right. So a quick observation on tree diagram on the screen here. So the differences of these three diagram is on the Reynolds number. Okay, so the first one, Reynolds number is 0.1 on the left. Middle, Reynolds number 10. Reynolds number 10 power 7. Again, what is Reynolds number? Reynolds number equal to rho VD divided by mu, or you can use characteristic length. You can use rho VL divided by mu. Okay, or you can use the kinematic viscosity, kinematic viscosity. Okay, then you become kinematic viscosity. Then you can write as rho L. Okay, rho L. But anyway, if you look at the Reynolds number definition, if the rho is fixed, D is fixed, kinematics, dynamic viscosity is fixed. The only changes is velocity. So the higher Reynolds number means the higher velocity. Okay, so Reynolds number is important when you're defining the characteristic of flow. As you can see here, as you increase the velocity or increase the Reynolds number, what do you observe from the diagram here? You will see that the gray color region is shrinking. Okay, the gray color shrinking is the gray area is shrinking. What mean by the gray area? Gray area is an area where the viscous effect take into place. Okay, viscous effect take into place, or you can say where you have the friction effect inside here. So as you increase the velocity, the viscous effect region is shrinking until it's so high then the boundary layer or the viscous effect layer region is very near to the surface. Okay, so this is what happened to your boundary condition when you increase the velocity. And at one time the region behind the flow we call it wake region. Okay, wake region. All right, so this what about this diagram. And then another one is a circulation on the object. In this case, it's a circular cylinder. So as you can see here, as a flow along the body, you'll see there's a streamline go up and down. And you see here, the first one is Reynolds number 0.1, means very slow flow. And as you increase to a bit higher, Reynolds number 50, you see that something happened behind the object. This is just a reference number. So at a certain scenario, at a certain velocity, there's a separation happening behind the object. Okay, as you increase in the laminar flow or in the very slow flow, you have a smooth streamline where there's no separation yet. But up to a level, up to a certain speed, the separation will happen and you have a flow back, separation bubble will take place. Means there's a flowing back to the body. So you have a separation bubble happen. Then as you go higher, you increase the speed. In this case, Reynolds number 10^5 is very high. You'll see that after the body, you will have a separation region, where here you will have a turbulence region, or we call it wake region happen. Okay, so this is a basic understanding on what happened to the boundary layer when you increase the Reynolds number. In this case, we use a round body as our case study. Okay, so there's a video. This one explain how this big giant bird here. The name for this bird is albatross. So albatross, it can float in the air at a very low velocity. Okay, so you can go and view this video later on. Okay, another one we call it, another one when you study flow over immersed body, you will come across this diagram. Now let me explain about this diagram. So you have a plate here, and as you have a flow along the surfaces, the object will build a region called boundary layer. Okay, this dashed line we call boundary layer. What mean by boundary layer? Boundary layer means a thickness of liquid that give you near to 99% of the upstream. Okay, let's say this one. let's say your upstream velocity is 100 meter per second, or your input velocity. Okay, your input velocity is 100 meter per second. So this dashed line here, or this dashed line here, although we cannot mark in the real case lah, okay, theoretical, we can mark all this line here. What mean by all this dot here? It means that it is 99% of your U, meaning this line here is have a velocity of 99 meter per second. In this case, I will give you a number. The number is 100 meter per second. It's not necessarily 100 meter per second, but the concept is this boundary layer line here is 99% of your upstream velocity. Okay, meaning how you plot. Maybe someone asks you, how do you plot the boundary layer on the plate with the velocity, upstream velocity, let's say 100 meter per second. You plot based on 99% of the velocity. So this one, when you plot, you try to measure the velocity above this plate, you get 99 meter per second. Then you plot. Then you get the shape of this gray area. Okay. And here you see the mixture of laminar and turbulent region. Okay. Okay, the rest you can read. So as you can see here, what I explained just now. Okay, I explained just now how you define the thickness delta or the boundary layer thickness is up to 99% of your upstream velocity. Thickness we measure in y, okay, in y direction. So we will put in as y. Boundary condition velocity that we mark as a boundary layer thickness, we use velocity 99% of the upstream, or 0.99. Okay. So the next one is more on the derivation on the uniform flow. So on the left-hand side diagram is a uniform flow. As you can see, the arrow at the bottom and the above one is the same. So the velocity doesn't change. So meaning there's no viscosity effect. And in this case, we use the delta star, mean the thickness is the same. It's a uniform profile. Then after that, the second diagram here is due to the viscous effect. So viscous effect means as you near to the wall there and you have friction, meaning you have zero velocity as you near to the wall here, and as you get further than the wall, you will get back your velocity. So this point here will give you 99% of your velocity. And then go up a little bit, you get 100%. Okay, so this is the curvature that we will get. And previously, I think we have derived how we convert the non-uniform parabolic flow into uniform flow. Right? There is a chapter where we discuss about this one. Okay, so the rest is more on the mathematics model. So we will look at flow rate. So this is more on the equal the two diagram here. We make some calculation based on their area. So if you take this one, thickness of this one, let's say this is your T, how you calculate area, you take B times U, okay? So what is flow rate? Flow rate is Q. What is Q? Q is V times A, velocity times area. Okay, so you take B. B is the width of the plate here. So you take thickness times the width, you get area. Area times velocity, you get Q. Okay, now how do you this one is from this diagram. This equation is on the left diagram. So you want to calculate the volume flow rate from the parabolic equation here. You take u minus ub times dy, then you integrate. Okay, this one is more on the integration side. Then you rearrange the equation, you'll get your thickness, boundary layer displacement thickness star in the integration format. Okay, star. Okay, thickness. So this one delta star is a boundary layer displacement thickness. Okay, star. How do you know the differences between star and without star? Star is a perfect case. Star is a perfect case where you equal the logarithmic case to an ideal case. Then you get this equation. All right. So important, this equation is important. So this one will enable you to simulate the boundary layer above a plate. So this equation is important when you use simulation software where you will generate the thickness for you. Okay, so they are using this equation to generate the thickness of the boundary layer. Okay. Another one, boundary layer, another type of boundary layer is called momentum thickness. Another layer thickness, it's called momentum thickness. Momentum thickness is used on drag only. It's often used for drag. You want to find what is a drag, then you use momentum thickness to determine. Okay, I'll go very fast. This one is the momentum equation. Okay, I'll go very fast over here. You look at the slides later. This is mathematic model, and this is the momentum flux equation. All right, then you rearrange the equation. You will get the momentum thickness equal to this equation. All right. So you have three types of boundary layer thickness. The first one, normal one. Second one with the star. The third one is like an omega shape. This one is a momentum thickness. So you have three types of boundary layer analysis. Either you find this one, or this one, or this one. Okay. All right. Okay, let's go for a short break. We will look at this example.